Did you know that Isaac Newton developed his laws of motion while observing an apple falling from a tree, pondering why it fell straight down and not sideways? This remarkable insight led him to formulate three fundamental laws that serve as the cornerstone of classical mechanics. Isaac Newton, a renowned English physicist and mathematician, revolutionized our understanding of the physical world. His laws of motion elegantly describe the relationship between forces acting on an object and its resulting motion. They are as follows. Firstly, Newton's law of inertia. This law states that an object will remain at rest or move at a constant speed in a straight line unless acted upon by an external force. It highlights the inherent tendency of objects to maintain their current state of motion, a concept known as inertia. Secondly, Newton's law of force and acceleration. This law establishes that the net force acting on an object is equal to the product of its instantaneous acceleration and mass. In simpler terms, it defines how the rate of change in an object's momentum determines its acceleration. Lastly, Newton's law of action and reaction. This law asserts that for every action there is an equal and opposite reaction. It elucidates how forces always come in pairs, with each force being the reaction to the other. These laws were initially introduced in Newton's monumental work Philosophiae Naturalis Principia Mathematica, published in 1687. They laid the groundwork for classical mechanics and have been guiding scientists and engineers in their exploration of the physical world ever since. However, it's important to remember that while Newton's laws are incredibly powerful, they do have their limitations. For high-speed scenarios, massive objects, or at microscopic scales, we need to turn to other theories such as special relativity, general relativity, or quantum mechanics. Newton's laws of motion, simple as they might seem, have profound implications for our understanding of the universe. Imagine sitting in a car that suddenly stops. You lurch forward. But why? Newton's first law of motion, the law of inertia, has the answer. In the grand tapestry of physics, Newton's first law, often known as the law of inertia, holds a place of prominence. It tells us that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. In layman's terms, objects don't like to change what they're doing. They resist change, a property we call inertia. This law was not born in a vacuum. It was built upon the foundations laid by earlier thinkers. Galileo Galilei, the Italian polymath, first formulated the principle of inertia for horizontal motion on Earth. René Descartes, the French philosopher, then generalized this principle. Their insights were rooted in careful observations and experimentations, like Galileo's experiments with balls rolling down inclined planes. In everyday life, we experience the law of inertia in various ways without even realizing it. When you're in a moving car that suddenly stops, you're thrown forward, not because an invisible hand is pushing you, but because your body wants to keep moving. It resists the change in motion. Similarly, when a car accelerates, you're pushed back into your seat. Your body at rest wants to stay at rest. This law also explains why we don't feel the Earth moving. We're moving with it, so to us it appears at rest. There's no distinction between rest and uniform motion in a straight line. It's all relative to the observer's perspective. So, Newton's first law, the law of inertia, is not just an abstract principle confined to the pages of a physics textbook. It's a fundamental aspect of our everyday experiences. It's in the lurch you feel in a sudden stop, the tug you feel in a swift acceleration, and the stillness you feel on our spinning planet. So next time you lurch forward in a car, remember, it's Newton's first law in action. Why does a heavier object require more force to move than a lighter one? Newton's second law of motion provides the answer. This law, often described as the law of acceleration, states that the force exerted on an object is equal to the mass of the object multiplied by its acceleration. Picture it this way: if you and a friend are each pushing identical shopping carts, but your friend is pushing twice as hard as you, their cart will accelerate twice as fast. This is the essence of Newton's second law, but how do we express this mathematically? In the simplest terms, force equals mass times acceleration, often written as F equals m times a. Here F represents the net force acting on the object, m is the object's mass, and a is its acceleration. This equation beautifully encapsulates the relationship between these three quantities. So, what does this mean in practical terms? It implies two things. First, the acceleration of an object is directly proportional to the net force acting on it. This means if you push a stationary object, it will start to move, and the harder you push, the faster it accelerates. Second, the acceleration of an object is inversely proportional to its mass. Consider trying to push a car and a bicycle. The car, being much heavier, will accelerate more slowly than the bicycle, even if you apply the same amount of force. Let's take another example. Imagine you're at a bowling alley. You effortlessly toss the lightweight bowling ball down the lane, and it quickly accelerates. But when you try to roll the heavier ball with the same force, it moves more slowly. This is Newton's second law in action, so the next time you're on a seesaw and can't lift your heavier friend, or you're struggling to push a heavy piece of furniture, remember, it's not you, it's physics. Newton's second law is at play, dictating that a larger force is needed to move a heavier object. So when you're struggling to push a heavy object, you're experiencing Newton's second law firsthand. Ever wondered how a rocket launches into space? Newton's third law of motion explains it. This law, often summarized as "for every action there is an equal and opposite reaction," is a simple statement with profound implications. When two bodies interact, the forces they exert on each other are equal in magnitude, but opposite in direction. This principle is the key to understanding a multitude of everyday phenomena. Consider the act of walking. When you take a step, your foot pushes backward against the ground. According to Newton's third law, the ground responds by pushing forward with an equal force. This forward force is what propels you to move. Without this interaction, you wouldn't be able to walk or run or even stand still. Now, let's take a giant leap from the ground to the cosmos. When a rocket launches, it expels gas at high speed in the downward direction. The expelled gas, in turn, exerts an upward force on the rocket, propelling it into space. This is Newton's third law in action on a grand scale. Newton's third law is not just a cornerstone of physics, it's a universal principle that governs the motion of celestial bodies and microscopic particles alike. It was introduced in Newton's groundbreaking work, The Mathematical Principles of Natural Philosophy, published in 1687. This work revolutionized our understanding of the physical world and laid the groundwork for the field of classical mechanics. However, even this universal law has its limitations. At extremely high speeds, massive scales, or minuscule dimensions, Newton's laws give way to the principles of special relativity, general relativity, and quantum mechanics, respectively. Nonetheless, Newton's third law remains a timeless pillar in our exploration of the physical world. It's a testament to the genius of Isaac Newton, who recognized the fundamental principles that govern the motion of all objects in the universe. So, whether you're walking or watching a rocket launch, you're witnessing Newton's third law in action. Newton's laws of motion have stood the test of time, guiding our understanding of the physical world for centuries. They have served as the bedrock of classical mechanics, enabling us to predict and explain the motion of objects in our everyday world with remarkable accuracy. However, it's important to acknowledge that while these laws are incredibly powerful, they do have their limitations. For instance, at incredibly high speeds, close to the speed of light, Newton's laws start to break down. This is where Albert Einstein's theory of special relativity comes into play, providing a more accurate description of the behavior of objects moving at such extreme velocities. Similarly, when dealing with massive objects that exert a strong gravitational pull, like stars or black holes, Newton's laws again prove inadequate. Here, Einstein's theory of general relativity provides a more comprehensive understanding, explaining how such massive objects distort the fabric of space and time itself. Moreover, on the tiniest scales of atoms and particles, the classical mechanics based on Newton's laws gives way to the strange and counterintuitive world of quantum mechanics, where particles can exist in multiple states at once and teleport through barriers. Yet, despite these limitations, Newton's laws are not discarded. They remain incredibly useful for most applications in our daily lives, and in many fields of engineering and science, they are the first stepping stone in the journey of understanding the mechanics of our universe. Beyond their practical applications, Newton's laws also embody a profound philosophical message. The universe is not chaotic, but follows certain rules, and through scientific inquiry, we can discover and understand these rules. So if you're intrigued by the elegance and simplicity of Newton's laws, I encourage you to delve deeper, explore more about physics, relativity, quantum mechanics, and how these theories continue to shape our understanding of the universe.